Right, so it's both a pleasure and an honor to be here and to speak. And I guess I have known Philippe since 2012, at least that's as far as I can remember. And obviously that's way less than most people in this room. But again, at the moment we met, I thought, this is a really cool guy. I would like to hang out more with him. And I hope that in 30 minutes I will be able to show you what precisely I mean by that. In the meantime, let me try to entertain you with some joint work with Philippe, Renat, Sergei Horoshkin, and Gus Schrader. And so I'm convinced that in this work there are no new results and no new ideas, and yet I think the packaging is rather cool, at least to me, so I'll try to share that. So the goal is to find wave functions of Ruchnar's integrable system, also known as eigenfunctions of McDonald operators. And well, obviously they're known, but we'll rederive them in some nice way. And the tools will be a certain representation of SL2Z, and this guy is called quantum cluster varieties. And sort of as in any, sorry, it's confusing. As in any sort of film, there will be the main hero or main actor rather. It will be the quantum open Toda chain. And today, so we'll have some group in the background. The group is SLN, and for the purpose of this talk, most of the time you can think n is equal to 2, unless otherwise specified. Right, so the first kind of chapter of this is this algebra called spherical Daha that most of you, of course, know better than I do. So I'll denote it as SHQT. This is spherical Daha for SLN. That's double affine Hecke algebra, and it's sort of an algebra that lives on a torus. And when I say lives on a torus, that means the following. It means that if we take the first homology of, well, actually punctured torus, if we take the first homology of the punctured torus, this is just isomorphic to a two-dimensional lattice, Z2. And for any element of this lattice, there will be a generator of spherical Daha. Moreover, we have a modular group of this punctured torus acting on spherical Daha in this obvious way that if you take an element from SL to Z and act on EV, you just act on this vector in Z2, and that's your generator that you get. And finally, the spherical Daha will be actually generated by, well, a finite collection of elements, EK0 and D0K, as K runs from 1 to n. Now, the way SL to Z appears in this game is the SL to Z is the mapping class group of the punctured torus, and mapping class group, let me just remind you, that's a group generated by Dane twists. So here I show an example of that. So if you have a closed simple curve, the green one, say, and take a Dane twist along this curve, so you cut along this curve, rotate 360 degrees and glue it back. And what you see here is the result of applying kind of this Dane twist along the green curve to the orange one. Right, so SL to Z is just group generated by those for a punctured torus. And another really important thing about the spherical Daha, so while it's somewhat complicated to, or I don't even know if they're known in closed form, the relations on the generators, what is definitely known is a faithful representation, or in other words, you can think of it as embedding into algebra of Q difference operators in variables lambda and variables t. So t is just a shift in lambda, right? If you commute ti and lambda j, it's q to the delta ij lambda j ti. And then the way you embed spherical Daha into this algebra of Q difference operators is EK0 is just sent to elementary symmetric functions in lambda. And since we work with SLN, we impose condition that product of all the lambdas is equal to 1. And E0K it goes to McDonald operator. I'm not going to write general formula, but for SL2, I can show it. So E10 goes to lambda plus lambda inverse. That's elementary symmetric function. And D01 goes to this Q difference operator. T is a shift, and this lowercase t is that central parameter in our field. Right. So, how would one hope to find eigenfunctions right away? Well, the strategy should be as follows, really. So you find some Hilbert space representation of spherical Daha, but you ask this representation to be SL to Z equivariant. And then if you have that, then you're in business, because what you can do immediately is the following. You can just take product of delta functions. And if you take this product of delta functions and you apply a multiplication operator, elementary symmetric function, right? What you get is just elementary symmetric function of x's, right? So this is an multiplication operator, and this is its eigenvalue, if you wish. And then what you can do, you can take an element of spherical Daha. So here I chose this 0, -1, 1, 0 element of order 4. Well, in SL version element for, well, 2 in representation. And then, or really instead, you can just take any element that sends vector 0k to vector k0, and, or yeah, sorry, vice versa, k0 to 0k, then E0k is just S applied to EK0, which just means that you take how EK0 acts in representation, conjugated by how S acts in representation. And then for this operator, which is E0k, your eigenfunction is just, you take your delta functions and apply to them this element S, right? So I'm really saying something from first year linear algebra, right? You conjugate your operators by something, means that you need to act on your representation by this something, right? So this is change of basis matrix. That's the only thing that happens. So if you can compute, if you have this SL to Z covariant representation of Daha, and you can compute how elements of the mapping class group act on this representation, you're done. You know how to compute eigenfunctions of McDonald operators. So that's the strategy. And in order to find such representation, well, we can actually look at, indeed, quantum cluster varieties, but they come from some geometric constructions. So let me present this construction. It's kind of really a story about these things called character varieties, right? So you start with a surface. It's a closed surface with some punctures oriented, and the group G. And then decorated local system is, well, first of all, it's a local system, which means it's a homomorphism from pi1 of the surface to the G. And second, for every puncture, you have a flag sitting at this puncture that is invariant under the monodromy around that puncture. So this is really discrete data, because if you have a, well, almost always, so if you have a monodromy that's generic, choosing this flag is just really just ordering eigenvalues of this monodromy matrix, right? The monodromy around that puncture. So that's a very mild kind of generalization of these local systems. Then this log GS is just space of such local systems, and PGS is a moduli space. So I just take all these local systems and mod out by group. And this little circle here just means that, well, I want this to be a variety, and G has stabilizers when it acts. So I kind of delete all the points when delete all the points where G doesn't act freely, make G act freely, and then get this decorated character variety, this PGS. Cool, so this variety actually has Poisson structure, so we can quantize it. And I'll call, so this OQ PGS is just quantized algebra of functions on this character variety. And gamma S is the mapping class group of the surface. And well, this mapping class group naturally acts on our character variety, and therefore it acts on quantization of functions on that character variety, right? So in case, our surface is actually a punctured torus, let me introduce one additional constraint. This additional constraint will be that I really don't want to look at generic monodromies. So we have a torus with a puncture, so we just think about monodromy around that single puncture. And I don't want it to be generic, but rather I want it to be of this special form. I want it to lie in this conjugacy class, which is Roosh-Schneider condition, meaning this is a scalar matrix plus something of rank 1, or equivalently, it just means that its Jordan normal form is just all coinciding eigenvalues except for the last one, and Jordan blocks of minimal possible Jordan blocks. And of course, if G is SL2, then this condition is void, right? Because we still have just lambda inverse. So for SL2, they're the same, but for SLN, this is some extra condition. And there's this kind of fact that I didn't really know who to attribute, because I guess anyone who thought about this setup came up with this. It's sort of that, well, the spherical Daha is really just isomorphic to this quantized algebra of functions on this character variety with this condition on the monodromy. I mean, part of this statement, it's not really a theorem that I'm saying here, right? It's part of this, of course, depends on which particular algebra you mean by, quantized algebra functions on the variety. It's just particular way of quantizing, but, it was made into a theorem in many different contexts. But indeed here, you kind of see how SL2Z action comes into the spherical Daha story. It's just this mapping class group that acted on the character variety, right? And these generators EK0 and D0K, they're nothing but traces of monodromies along sort of A cycle and B cycle, the green and the orange one. And if I am in SL2, I just take a trace. But if I'm in higher rank, I take trace in kth fundamental representation, and that gives me EK0 or E0K respectively. So that's really what spherical Dacha is. And the next slide is, this guy's called quantum cluster varieties, so I'm not going to explain what they are, but I'm going to explain what they, what tools they provide for us. So this cluster varieties, at least one version thereof, it's actually a Poisson variety, and so you can, there is some canonical way to quantize those. It's called quantum cluster varieties. I denote them LQ. And part of the package of this cluster data is certain thing called cluster modular group. And these quantum cluster varieties, they actually come with a Hilbert space representation, which is equivariant with respect to this cluster modular group. So this is precisely the setup we wanted, so precisely the data we need. And the upshot, of course, is that this character variety that is related to Dacha will actually be a cluster variety, and therefore will get this mapping cluster group equivariant Hilbert space representation. And this is sort of done in works of Fock and Goncharov, and for SL2, of course, you can just read their works and get this package that we needed. But for SLN, there's this extra condition on sort of your monodromy being reduced, and this is really what Gus, Renat, and Philippe we try to establish cluster structure on this reduced moduli space. But again, for when n is equal to 2, when we're talking about SL2, that's just the standard for Goncharov story. Right. And in other words, to summarize what I just said, we're trying to construct an embedding of spherical Dacha into this quantum cluster variety. And then if we have representation of the quantum cluster variety satisfying all these properties, we just pull it back to subalgebra, spherical Dacha, and yeah, we're done. So indeed, let me rewind. Spherical Dacha is generated by EK0 and D0K, and in some faithful representation, EK0 becomes multiplication operator by elementary symmetric functions, and D0K become McDonald operators. On the other hand, this target algebra, this quantum cluster, quantization of functions on a cluster variety, also have certain operators, LK0 and L0K, let me call them. And so this is some new thing that I'm telling now, that in this representation that I claimed these cluster varieties have, these operators, the LK0 will actually become Toda Hamiltonians. Hamiltonians of quantum open Toda chain. And L0K, well, they will become some operators that depend on, position operators X, momentum operators P, and this extra variable T. And this extra variable T also has geometric meaning. This is this eigenvalue of the monodromy around puncture on the torus. So that the T also is a geometric origin. And we need to sort of relate these two representations, and the starting point is just to remember that Toda Hamiltonians have elementary symmetric functions and their eigenvalues. So the first thing you should try to just take this representation and diagonalize Toda Hamiltonians and see what happens to this other set of operators. And lo and behold, lo and behold is postponed until the next slide. But right, so let me talk about diagonalizing Toda Hamiltonians. So there is this very well-known functions called Whittaker functions or Q-Whittaker functions. They're joint eigenfunctions for Toda Hamiltonians. So if you apply Toda Hamiltonian to a function, so it's a function that depends obviously on position operators, but also has some variables lambda that tell you the eigenvalue. So if you take Toda Hamiltonian, it's an operator, remember, in x and d over dx. Applied to this function, you get, it's the same as just take this function multiplied by elementary symmetric function of lambda. So this is the eigenvalue of Toda Hamiltonian. And here and in the rest of this talk, when I write uppercase letter, it's just lowercase, the exponent of the lowercase letter. Right? And there's the theorem proved for SL2 by Renat Kashayev and SLN by Gus and myself that this process of diagonalizing Toda Hamiltonian really provides a unitary equivalence between two Hilbert spaces. So the first one is the space of this representation that comes from quantum cluster varieties. So it is L2 space on Rn, just with the standard Lebesgue measure. And the second space is sort of symmetric functions in Rn with Sklenin measure. So these are, and in my notations, these are functions of x, these are functions of lambda. And the Whittaker transform, this W here, this is just like Fourier transform, but you use Whittaker functions instead of plane waves. So really you just change basis to an eigenbasis of total Hamiltonians, the only thing that happens. And you can check, so we prove that it's a unitary equivalence, and now the kind of important bit, of course, is that this other operator, so this so you had one cycle and the other cycle. One cycle you diagonalized, it became multiplication by elementary symmetric functions. The other cycle that was written in some complicated L hat operators, they become McDonald operators after you applied it to Whittaker function. So under change of basis, one representation becomes the other. And so let me once again summarize what I just said. So it's a theorem that for n equal 2, it's a folklore rather than, anything else. And for n equal 2, it's something that we've figured out with Philippe, Renat, and Gus, is that indeed you have an SL2Z equivariant injective homomorphism of spherical Dacha into this quantum cluster variety. And the homomorphism goes as follows. So you have, and in both cases, you have these operators that correspond to traces of cycle A and cycle B. You just send traces of cycle A to traces of cycle A, and same for cycle B. Right? And what's the idea of the proof, right? So you have two algebras. So first of all, what's the problem of constructing a homomorphism? Well, the problem is that in this algebra, you at least know the generators, but you don't know relations. In this algebra, you know neither generators nor relations. It's a bit hard to construct maps between them. But luckily, you know faithful representations. So what you do, you kind of embed this algebra into some operators on this Hilbert space, and same for this algebra. And then you have a unitary equivalence between these two Hilbert spaces that intertwine your action. So you take generators for spherical Dacha, see how they act on here, see how they act on this space under the unitary equivalence, and recognize them as action of some elements from the quantum cluster variety. This way you get an embedding of spherical Dacha into this quantum cluster variety. So you get what we wanted. You get an SL2Z equivariant representation of spherical Dacha, where action of the mapping class group can actually be effectively computed. And here's sort of a scheme on how we're gonna diagonalize McDonald operators now, right? So over here, this is just for SL, I've just spelled it out for SL2. So over here we have this representation space of spherical Dacha, sort of it's kind of Cherednik's representation, but instead of acting on polynomials, we now act on more general functions. So we have elementary symmetric function, lambda plus lambda inverse, and we have M1, this is just McDonald, the first and only McDonald operator in SL2. On the Whittaker transform, this E10 becomes L10 hat, which is a Toda Hamiltonian, and E01 becomes some operator that's, well, it's a bit hard to recognize, and I don't know what it is in general. Then you apply the S transformation, because remember, this representation of quantum cluster variety, this is SL2Z equivariant. So here we can apply actually S transformation, and under S transformation, of course, L10 becomes L0 minus 1, and L01 becomes L10, right? So when we went from here all the way to, from upper left to lower right, your McDonald operators became Toda Hamiltonians, right? But then you can even play this game a bit further and diagonalize Toda Hamiltonians, and this way McDonald operators become just elementary symmetric functions with the eigenvalue e to the, some parameter mu plus e to the minus mu, right? And what does it mean? It means that eigen function for McDonald operators, you can construct it as follows. So you take eigenfunction for a multiplication operator, which is a delta function. You apply inverse Whittaker transform, which is integrating against a Whittaker function. you apply S transformation, and you apply Whittaker transform, which is integrating against complex conjugate of the Whittaker function. And really, the only thing that's written here is just written, it's a matrix coefficient of this S transformation, so of an element of the mapping class group in representation of SL2Z that comes from this quantum cluster varieties. And it's a matrix coefficient of this operator S evaluated on two Whittaker functions. So just to summarize here, if you apply McDonald operator to this phi, you just get e to the mu plus e to the minus mu times phi, right? So this is precisely saying that this is an eigenfunction for McDonald operator. And here, and once again, I sort of used the logarithmic. Tau is sort of a log t, if you wish, up to multiplying by t. Right.
Just so you know, if you want time for questions, then you have about 4 minutes left.
All right, I'm almost done.
9 minutes if you don't want time for questions.
I'll consider that, thank you. Oh, sorry. Yeah, right. And corollary is, well, one simple corollary that's, again, not news, of course, but you can get all kind of sort of dualities for free, right? So the duality as mu goes to minus mu or lambda goes to minus lambda. This is just the fact that Whittaker functions were symmetric in spectral parameters, so that's for free. This equality, it's sort of a mix of kind of two different McDonald dualities, but this equality just comes from the property that we can think of McDonald eigenfunction as a matrix coefficient, and knowing that S is, well, this for SLN, it's a unitary operator of finite order 2 in fact here, but it works for GL as well. And indeed, this formula, this matrix coefficient, recovers known formulas for McDonald eigenfunctions, so those that appeared in Halnas-Ruchinar's works, or recently Belosov, Dergachev, Kharchov, and Haroshkin. And then, okay, fine. So, but we started with McDonald operators. If you want to really get McDonald polynomials out of it, what do? Well, really, you just take your function, which is, of course, not a polynomial, but then you evaluate it at special values of mu, and you do that by some sort of residue count, and you actually recover McDonald polynomials. So this is a way to kind of recover McDonald polynomials from this scheme. And conclusion of this part of the talk, and I'll have a second part of the talk, I'm sorry, I know about 2 minutes left, is that, right, so if we have an SL2Z equivariant Hilbert space representation of spherical Dacha, then we can get Ruchinar's wave functions by some kind of more or less obvious procedure by taking delta functions and writing them in different bases, well, applying change of basis to them. We can get McDonald polynomials by some residue count. Quantum cluster varieties indeed provide such representations. And of course, and in fact, you don't have to do it just for spherical Dacha. You can do it for all kind of different algebras, like quantum groups or duals to them, or Esky-Wilson algebras, and so on and so forth. So this is sort of an ad for this recipe. And of course, what we would love to do is somehow approach McDonald theory via these methods. But of course, then you'd have to somehow study not, you know, McDonald polynomials themselves, but modified McDonald polynomials. That's not in work in progress, but ideas in progress. So let me know. I'll get ahead of myself. And that concludes the first part of the talk. And the second part of the talk is, well, Philippe, I wish you a very happy birthday. And previously, I had a different slide here. It was, so this gentleman here is, or this comrade here is Stakhanov, Philippe's role model. And you know, the famous photo of him is he with a jackhammer, because, well, again, I believe most of you know who this guy is, but just in case, I saved it from Wiki. So in 1933, Stakhanov became a jackhammer operator, so Philippe's role model, obviously. And in 1935, he took a local course in mining. On the 31st of August in 1935, it was reported that he had mined a record 102 tons of coal in 5 hours and 45 minutes, speaking of Philippe's 170 papers published in I don't know how many years, which was 14 times the quota, which, Philippe, I think fully applies to you. So in here, moreover, so he was granted a car, as far as I understand, for his birthday by Soviet government, and I don't know why he's pushing his own car. I hope that never happens to you, so that's my birthday wish. And that concludes the second part of the talk. And the third part of the talk is actually a video that I wanted to show, and apparently I need to make some sign, I don't know. And this video, you will probably recognize some people in the room on this video, and that's from 2012 when I think Philippe and I first met. I think. So yeah.
Это есть наш последний и решительный бой. С интернационалом воспрянет рот.